here is something that sounds entirely made up. Over the past several years, China has quietly directed more than $1 billion into glass, not semiconductors, not rare earth materials, not the next generation of lithography equipment, glass, and because of that investment, some of the most powerful technology companies on the planet are now scrambling to catch up in a competition. Many of them barely registered had begun. Before you assume this is about display panels or phone screens, stay with this. The glass at the center of this story bears no resemblance to anything you have ever handled. It is engineered to a level of precision that would have seemed implausible 2 decades ago, thinner than a human hair, flatter than anything that forms naturally, and potentially the single most important material in determining who controls the next decade of computing power. The strangest part is that none of this was concealed. The factories, the patent filings, the investment programs, all of it was publicly available. It simply was not being watched, because almost everyone focused on the global chip race was staring at the same thing. Transistors. Who could make them smaller? Who could print more of them? Who could reach the next node first? While that loud and expensive conversation dominated every headline, a quieter conversation was unfolding about the layer beneath the chip, the part that holds everything together. That layer has become one of the most consequential battlegrounds in the entire industry. To understand why glass matters so much right now, you need to understand what it is replacing. Picture a modern city, towers, transit networks, power infrastructure, fiber running under every street. You can appreciate the engineering above ground all you like, but none of it functions at the foundation beneath it shifts. And the moment the ground moves, everything built on top is compromised. No amount of clever design at higher levels can compensate for an unstable base, and computer chips have a foundation too. It is called the substrate, the base layer the chip sits on. It holds components in position, routes electrical signals between them, and helps manage the heat generated during operation. For roughly 50 years, these substrates have been made from engineered plastics and resins, layers of synthetic material bonded together into something resembling sophisticated laminate, not glamorous, not the subject of marketing campaigns, but essential in the same way concrete footings are essential to a building. For most of chip history, plastic was adequate. Early chips were compact, demands were modest, and the substrate performed its job reliably. The trouble started when chips became dramatically more complex, and force driving that complexity was artificial intelligence. The chips powering today's most advanced AI systems are not single monolithic devices anymore. They are clusters of smaller chips called chiplets, bundled together into one densely interconnected package. Engineers build them this way because it allows different types of chips, memory, processing, communication logic, and each optimized for its specific role, to be combined into a unified system that performs far beyond what any individual chip could achieve. It is genuinely clever engineering, but it created a problem that compounds as these systems grow larger. Some chiplet packages now extend beyond 8,000 square millimeters, minus roughly the footprint of a smartphone screen, packed with billions of microscopic connections exchanging data simultaneously at speeds measured in hundreds of gigabytes per second, while generating enough heat to shut down a laptop in seconds. At that scale, the substrate stops being a passive structural element and becomes one of the most critical performance variables in the entire system. Plastic warps. When a plastic substrate heats up during operation, it expands slightly, and when the chip cools, it contracts. That cycle repeats thousands of times across the lifetime of a device. Each individual movement is almost imperceptibly small, shifts measured in fractions of a millimeter. But at the scale of a modern AI package, where connections are finer than a strand of DNA, those tiny movements accumulate into a serious problem. Connections that were perfectly aligned during manufacturing begin to drift. Signals distort, performance degrades in ways that are inconsistent and difficult to diagnose. In the worst cases, connections fail entirely. The most maddening aspect is that none of it is visible. There's no obvious crack, no clear moment of failure, just silent degradation until the chip stops working. Engineers addressed this for years through design, ingenuity, tighter manufacturing tolerances, and increasingly sophisticated quality control. Those approaches held while chip packages remained relatively small. But the next generation of AI hardware is entering territory where those workarounds simply cannot hold. The substrate material itself had to change, and the answer the industry arrived at after years of materials research. Failed attempts and incremental manufacturing breakthroughs still surprises people when they hear it. Glass is such a counterintuitive solution that it is worth pausing on how strange it initially sounds. Engineers are proposing to build the foundation for the world's most powerful AI systems, machines operating at extreme speeds, under extreme thermal loads, running workloads worth billions of dollars, using what sounds like the material swept off a kitchen floor, except it is genuinely not the same material at all. The glass used in next-generation chip substrates is a precisely engineered product developed specifically for semiconductor packaging. It shares basic chemistry with window glass in the same way a Formula One car shares the basic concept of a bicycle. Technically related, practically an entirely different thing. The clearest way to understand what makes it valuable is this. Plastic under repeated thermal stress behaves like a rubber band. Heat it, cool it, cycle it repeatedly, and over time it loses dimensional consistency and becomes unpredictable. Glass under the same conditions behaves more like a steel rod. You can run it through thousands of thermal cycles, load it with mechanical stress, and it barely moves. Its dimensional stability is dramatically superior to any plastic currently used in chip packaging, and that stability has a direct measurable consequence. Because the foundation does not drift, engineers can place electrical connections far closer together without concern that they will fall out of alignment over the chip's operating lifetime. And the figure that tends to stop people is this. Glass substrates can support up to 10 times the interconnect density of today's best plastic substrates. Not 10% more, 10 times more. That is not an incremental upgrade. 10 times more connections in the same physical space means chips that move data faster with less energy lost in transit, across greater distances within the package, with cleaner signal quality than anything plastic can deliver. This matters more than it might initially seem because the performance of an AI chip is not determined solely by its transistors. It is also determined by how efficiently data moves between components. If the connections between chiplets are slow, lossy, or limited in density, the chip underperforms regardless of how advanced the transistors themselves are. The substrate is the communication backbone of the entire package. Improve it substantially and you improve the whole system without altering a single transistor. So why didn't the industry move to glass a decade ago? Because manufacturing it is extraordinarily difficult. The glass must be flat to tolerances invisible to any instrument outside a specialized metrology lab. The holes drilled through it to create electrical pathways called through-glass vias are thinner than a human hair and must be placed with exact precision. Drilling those holes without introducing microscopic fractures that propagate and cause failure weeks after deployment is a manufacturing challenge that has taken years of dedicated engineering just to begin solving. That difficulty is not a footnote. It is the entire reason this story matters. Whoever solves the manufacturing problem at scale controls the next critical layer of the semiconductor supply chain. For most of the past decade, the dominant narrative in the global chip race centered on a single machine, the extreme ultraviolet lithography system produced by the Dutch company ASML. It is the only equipment on Earth capable of printing transistors at the most advanced scales. Export controls were constructed around restricting access to it. The logic seemed airtight without advanced lithography. No advanced chips. What that framing missed is that it assumed one specific path to more powerful computing. Advanced packaging, and the substrate layer specifically, represents a different path entirely. It does not require an ASML machine. It requires material science, precision manufacturing, process engineering, capital, and patience capabilities that can be developed independently without access to any export-controlled equipment. Seen through that lens, directing serious investment toward glass substrate technology is not merely a technical decision. It is a strategic repositioning toward a segment of the supply chain where the competitive rules are fundamentally different. China's national semiconductor investment programs have been steering capital toward advanced packaging since approximately 2023, with multiple companies and programs all targeting glass substrates. The total has crossed $1 billion across factories, equipment, patents, and engineering talent, none of it classified, all of it publicly registered, and largely ignored in Western coverage because the coverage remained fixed on lithography and transistor nodes. The company that brings this strategy into sharpest focus is BOE, one of the world's largest producers of display technology. The precision glass panels inside hundreds of millions of smartphones, televisions, and monitors each year require large-scale precision glass infrastructure, specialized equipment, deep process knowledge, and engineering expertise built over decades. That capability overlaps significantly with what semiconductor-grade substrate production demands. The equipment is related, the process knowledge transfers, the supply chains are already in place. And for BOE, this is not a reinvention. It is an extension of capacity already built at massive scale for a different application. Their program targets production-capable output running into 2026 and accelerating from there. The response from the United States, South Korea, and Japan has been more substantive than most outside observers recognize. Intel carries the longest track record in glass substrates of any company in the world, with a program extending back over a decade and one of the deepest patent portfolios in the field. More recently, Intel has shifted toward licensing, positioning itself as the intellectual property foundation of the emerging glass ecosystem, capturing value from every production line built on its technology, regardless of who operates it. Samsung is further along in production readiness than is widely appreciated, running an active pilot line at its Sejong facility with engineers hired specifically for glass substrate work. Its internal roadmap targets commercial-scale production around 2028. TSMC, which controls roughly 90% of the world's advanced AI chip packaging capacity today, revived its glass substrate research program in 2024, a clear signal that this technology had moved from interesting experiment to genuine strategic priority. When TSMC treats something as a priority, the rest of the industry pays attention. What it all adds up to is a race that remains genuinely undecided. No single company or country has established commanding control over the glass substrate market. Infrastructure is being built simultaneously across multiple continents right now, but the window for establishing durable leadership is not unlimited. The most consequential shifts in technology almost never look consequential while they are happening. They look incremental, technical, suited to a trade publication rather than a front page, and then years later, everyone who missed them looks back and sees clearly what was in front of them all along. The substrate is being reinvented right now, and the consequences will ripple through everything that runs on advanced chips: AI training, data center economics, drug discovery, climate modeling, scientific computing across every discipline. These are not hypothetical benefits. They follow directly from the performance gains that glass makes possible. The economic reality that makes this window difficult to recover from if missed is stark. A single glass substrate production line costs between $500 million and $1 billion to build, and takes years to qualify with customers because chip designers must validate that the substrate performs reliably at scale before committing their products to it. Whoever reaches volume production first enters that qualification process first. Whoever qualifies first earns the design wins. Whoever earns the design wins accumulates the production experience that improves yield and reduces cost per unit, which enables more competitive pricing, which generates more volume, which generates more experience, which improves yield further. The compounding loop tightens with every year of production, and companies outside it do not simply remain behind, they fall further behind each quarter. It is precisely the dynamic that transformed TSMC from a contract manufacturer in the 1980s into the irreplaceable backbone of the global chip industry by the 2000s, not through a single dramatic breakthrough, but through consistent early investment in a capability that compounded until no competitor could replicate it. The silicon era is not ending. 50 years of progress driven by shrinking transistors continues, but it is being joined by a second axis of improvement that does not depend on making transistors smaller at all, one that depends on making the foundation beneath them dramatically better. And the material making that possible has existed for thousands of years. The AI era may well be built on glass. The race to own that foundation is being decided between now and 2028, not in policy debates, but in factories being constructed, supply agreements being signed, and patent portfolios most people have never heard of. The decisive move in technological competition is rarely the one everyone is watching, and this time it may be the one hiding directly underneath everything else.